Alright, good. So you are most welcome again. We are in for item 006. Without wasting time, we are still moving on with our series of revision items as far as physics is concerned. Please visit the playlist. We have them right there from 001. And please, still in the playlist, we have got mathematics, we have got physics, and we have got chemistry. Feel free to visit our channel and look through what may be of importance to you. Okay, in simple terms, don't always forget to subscribe, okay, comment, like, and share. Please, especially sharing. We are now in the time whereby our candidates are soon going to sit for their mocks. Please, as a teacher, you may have this video helpful. You get down the question and you try it out with your students. You revise with them so that they get to know the answering techniques and how to go about some of the questions. I know as of now what is the difficulties within us, we as teachers, is that we may not have enough of the scenarios as far as some topics are concerned. That's why as Teacher Mtanda, we chose to always bring you some of the topical based items and with their solutions and in a well explained way. Without wasting time, let's get there. All right. Okay, please. So we simply remind you to share, like, and also comment. Like, share, and also comment. Okay, let's go there. Okay, good. So we have our question here already. So they're saying, okay, I'll get some laser pen. Where are you? Wait. Okay, so I think a certain landlord recently finished constructing a block of 2 houses and consulted an electrician to connect the houses to the electricity grid. Now, what do you mean by electricity grid? Those are the electric poles you see from place to place as you are moving on the roadsides or anywhere. That we call electricity grid. Okay. The electrician informed him that the voltage of the electricity needed to be stepped down from 30 kilovolts to 240 volts before connecting the houses. Okay. The landlord thought the electrician wanted to cheat him, so he decided to hire another person who was not qualified, or in a way that is bad, who is not qualified to do the job since he was cheaper. You should avoid this, please. You should always avoid this. The houses were connected in a way that a breakdown in one house could affect all the houses. The tenants complained that the current was so low and some of their appliances could not work. The tenants have threatened to vacate the houses if he doesn't work on the problem. Given that the appliances in the houses are connected such that the effective resistance in the room in the house are 10 ohm and 12 ohm. Okay, so the resistance they're using is 10 ohm and 12 ohm. Okay, all right. Use your knowledge of physics too. I think let's read it here. Use your knowledge of physics to explain to the landlord why stepping down voltage is required and how it is done. By the way, whenever you see this word stepping down, then you just know automatically you must talk about what you call a transformer. But maybe I'll briefly talk about what you call stepping down and stepping up. Please, a transformer is made in such a way that they will get a soft iron core like this. Now, what will happen is they will come and wind up some. Alright, they'll come and wind up. Okay, we'll get a different car here. I want us to know what. Whenever you see the word stepping down, then you just know we're dealing with transformers. So, okay, they wind up some wires here. There's some wires they wind up here, at this area here. They wind up some wires there, then also wind up some wires here, like that. Now, that's what we call a transformer in simple terms. However, the transformers are in two. We have what we call a step down transformer and a step up transformer. Now, what's the use of the word step down? Just like the word is step down. Now what you must know is that before we go any further, realize that as far as transformers are concerned, or as far as our home consumption is concerned, you find that those electric wires you see, the electric poles you see, carry around 13 kilovolts, or even the pylons. You all know what to call pylons. A pylon can carry around 13 kilovolts. 13 kilovolts is more like a 1000, in fact 13,000 volts on it. However, at home, even when you're charging your phone, the home appliances require only 240 volts. So it means that if they bring 13,000 volts, that would be an excess and will lead to accidents or burning down of the house. So it means that we must find a way of reducing this, bringing it down. And which device brings it down? We call it a step down transformer. Then we want to see, now here we're going to talk about strictly a step down transformer and how it works. I think let's go there. Okay, without wasting time, let's start part A. So you're saying that the voltage of 13 kV is too high since most of the household appliances use a less voltage. Now let's draw our transformer first of all, then we shall get everything explained. Okay, that's our soft iron core. All right. Right, we get it drawn. We get it drawn, please. We get it drawn. We get it drawn. Okay, get this there. Get this there. Put this there. Put this there. Okay, we label. Put it there. Next, we label that. We call it a primary. Okay, coil. And this one we call it a secondary. Right, coil. Okay, that one we call it a soft iron core, where those ones there are wound. All right, then we have everything done. However, let's make some improvement here so they can put some differences there. Okay, now what you must know is, let me explain here. You all know that in transformers we have it that in the transformer on this side we have two things. We have the voltage. Actually, we have what we call a primary coil and a secondary coil. Now this is the soft iron core. This is the soft iron core. This box like stuff here, like this. The soft iron core, like that. Soft iron core, like this. Then they come and tie. I will call it tying for simple understanding. Tie around some wires around it. Now these are the wires we have. You see this one coming like that, there, comes back there, goes 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 there. Then same way here, same way there. They are tying those wires around the transformer. Now what you must know is about a transformer, please, whenever you look at any transformer, you must pay attention to the number of, or the amount of wires wound here. The number of wires wound here tells you which type of transformer you're dealing with. Now those windings we have there, we call them what? Okay, we shall call it letter N. The windings we shall call them letter what? Letter N. Remember, this one is a secondary coil, primary coil, and a secondary coil. Now what we call a step down transformer, a step down. Then you have what we call a step up. Now in a step up, you find that the number of turns in the primary coil are greater than the number of turns in the secondary coil. Take it as this one is NP, this is N what? S. If you find that the number of turns in the primary coil are greater than in the primary coil is greater than the number of turns in the secondary coil, that was a step down transformer. Then if the number of turns in the secondary coil are greater than the number of turns in the primary coil, this one becomes a step up transformer. After that, it makes some sense. Now you see that here we have very many and then a primary coil compared to few and then a secondary coil. Therefore, that will become what we call a step down transformer. Just like these people also want to step down their transformer. Now what you must know is an example of the step-down transformers. They're the ones you see between electric poles. If you've ever seen that, you see two electric poles, then you see a transformer midway. They're like that. They're the ones we call step-down. Their work is to reduce on the amount of voltage, to bring down the amount of voltage. Like, say for example, from 13 kilovolts to 240 volts, which can be consumed by a house. By the way, what you must know is that for any proper house to work, some houses either use 220 volts or 230 volts. But as far as Africa is concerned, Africa for us we use more of 240 volts in a given homestead. But when you go to countries like USA, then they always use these variations here. Or if you buy a gadget which is from, say for example, India or China, you'll have this kind of labelings, 220 or 230 volts. So this one is better. So it means that if you receive 500 voltages, 500 volts, then it can easily cause what you call an accident or burns in the house. So you need a step-down transformer, which will get the 13,000 volts, of course 13 kilovolts, to 240. What can we use there? Is a step-down transformer. What is a step-down transformer? Number of turns in the primary coil are greater than the number of turns in the secondary coil. That has really made some sense. Then I know now someone will ask, when do we use the the step-up transformer? Please, a step-up transformer is used especially if they are to transfer, like say for example, we are in Uganda and maybe we are to transfer our power into maybe Kenya. Now there they need some step up, because you know that as these wires are moving from Uganda to Kenya in different districts, they are being consumed. So you know that in order for them to be able to reach Kenya, they must step up. Step up means that you can be having 500 volts and the transformer has got that gadget which can multiply these volts into around maybe 15,000 volts. So now a step up transformer is only used for power transmissions in longer distances. That's what we call a stepped up transformer. Maybe we want to take a look at them. Let's go there and see. Oh, sorry. We have this. Oh, wait. We'll have this. Okay, maybe we first go on. Shall I come back to that? Alright, good. So let's maybe see how the step-down transformer works. Then we shall move slowly. So now we shall say that when an alternating voltage moves through the primary coil, it induces a varying current which also flows through the coil, through the coil. Okay, now you find that get this is the disturbing us. All right, so what you must know about a transformer is that I'll explain in simple terms, then we shall get the writings later. So you realize that this is the load. Now this load is maybe the homes which are receiving that power. So you find that there will be some voltage here which is coming. Maybe this is our 13 voltage, 13 kilovolts. Now when they go through the primary coil, when they go through the primary coil of the transformer, you realize that these windings here, since there is a soft core, will make the soft core to be magnetized, because this is under electromagnetism. Will make the iron core to be magnetized, and you realize that from Fleming's rules, you realize that if you know the direction of the field, then you can tell the direction of the current like that. So find that when in simple terms, what you have here is once the voltage at this point alternating. Now this one means alternating. This symbol means alternating. That symbol is simply that alternating current. That's why I say that when alternating voltage moves through the primary coil, we have it here, because I explained this is where the voltage is coming, maybe from the power supply, from the electric pole, via the transformer to the load, which is maybe more like your home. Okay, it induces a varying current which flows through the coil. So you find that due to once the PD comes in, you find that there will be a current. A current will be generated. A current will be generated, and then that means that once you have current now start flowing. Let's do this step. All right. Maybe first of all, before we go there, I want us to see the picture. Now this one is an example of what we call a step down transformer. This is an example of what we call a step down, all right, transformer actually. Then a step up transformer is this one. I guess you've all ever seen this. And then I said this one is used if there are step up transformer. So for example, if you have 240 volts and you want to increase it to 13 kilovolts, you can use the step up. But if you have a 13 kilovolts and you want to take it to 240 volts down, to take it down, use a step down. So this one is a step down. A step down. This one is the step up transformer, like that. Let's finish up our okay. Okay, let's have it all here. So you're saying that the changing current induces a changing magnetic flux in the primary coil. Okay. Lastly, let's have it all, then we get it explained. The changing magnetic flux links up the secondary coil with less turns, which induces a lower voltage in the secondary coil. So I think let's go back there and see what this means. So you see that the changing current induces a changing magnetic flux in the primary coil. Okay, the changing magnetic flux links up with the secondary coil. All right, so okay, let's go back there and we get this explained. Good enough, have it in our written work. Let's go back there and see how we can explain better how a transformer works in simple terms. Okay, please. What happens with the transformer here is, in simple terms of this. Okay, now what you must know is that this is an alternating current being allowed in here. Alternating current being allowed in here. It means that this current can move in this order, like that, back there into the coil, moves in that order, like that, like that, like that, like that, and then back here. That's how it moves. But remember, we said it is alternating. Alternating means that it keeps on changing from time to time. So just like it was going like that, then still after some little time you find that this current again will change the pattern, and instead of going in this direction, instead of this going in that direction, again it will change the direction to that. Okay, it will come from again down, come like that via the coil like this. But this happens, they can't, of course one may think, won't they move and meet each other? No. What you are seeing different colors, just see that this happens at different time. Just like you see, you have it that we have got the clockwise like that. Okay, like this. That's what we are meaning. When this one is moving, this one is not there. When this one moves like that, okay, they move like it's a to and fro movement of the current. Now, as the current is moving, remember at one time, maybe just imagine at one time the current comes flowing downwards. Then that is the first cycle. Then another cycle, the current comes when it is going up. It is please, we are calling it an alternating current, meaning that it keeps on changing from time to time. If I have maybe I'll put a difference between a DC and an SC. What we call a direct current and an SC. It means that a direct current will go in one direction, just like you're seeing there. Then, but for alternating current, you find that current can go, like, say for example, like this for some 5 seconds. Then after the next 5 seconds, you'll again see the current coming back. It is a to and fro movement. To and fro movement keeps on changing. To and fro movement. To and fro movement. More like an example I can give is that maybe locally, how I can explain is that if you've ever seen a faulty bulb which blinks, gives light, goes off, gives light, goes off. That's more like what you call alternating current. Light on, light off, light on, light off. That's what I mean. Now, that kind of disorganization, the to and fro movement of current. A man called Faraday, we all know that from Faraday's law, that if, say for example, if there is a change, now, whenever you all know that a current carrying conductor, for any conductor carrying current, there is always an induced magnetism. We have an induced magnet. You can get an induced magnet from a current carrying conductor. So it means that here, what will happen is that in these coils here, we shall develop what to call magnetic flux. I think let me read this off. In this coils here, we shall develop what to call a magnetic. Okay, sorry, move this. Okay, in this coil, we shall develop what we call magnetic flux. Maybe we have that flux in that order, and we have that flux in that order. Now, why the flux? It's because current comes in that order, comes back there, goes up this level. After reaching there, again it comes back, follows its path, original. It's more like just as if the current moves like this via the coils to that. After reaching there, again it comes back via the coils to that. After reaching there, again it comes back via the coils to that. That's what we mean by SC. Now, in simple terms, what happens is, I'm explaining how the magnetic flux come about. Please, what you call magnetic flux, you have all ever drawn a magnet like this. Then you have got a north pole and a south pole. Magnetic flux, those are lines you are drawing like that. Those are the ones we call magnetic flux. So, you realize that here, and since the coil is carrying, the coil is carrying current, then therefore there will be an induced magnet. Okay, so maybe these are the flux. The flux are showing that there is an induced magnetism. Now you realize that in the flux also go according to how the current is moving. Maybe you find that if the current is moving in that order, like that, then here we shall have maybe south pole, and then we shall have north pole. Okay, now what this means is that since this coil has gotten magnetized the primary coil, now the primary coil is the one which receives current from the electric poles. Then this side, the secondary coil, is the one which delivers into our homes in simple terms. Now we want to see how does it step down. Now you realize that here it means that the magnetic flux will be flowing in that order, from north to south, from north to south. Now since this part here is magnetized and this one here is a soft iron, you find that the whole soft iron here will get what? Magnetized. Will get magnetized. And now we know that from Faraday's law, the EMF induced in the cell due to change in the flux is given by, we all know that from Faraday's law, the EMF E induced in the coil is given by the change in EMF over the rate of change of the EMF, but here we have a negative. This will be very important. Now, I was also explaining, since we have this magnetism here, and now we have taken it that the current is coming from up down, then it will be going in that order. But again, what you should know, as it comes here down, it comes back. I'll use another color here. This is a bit. So it will again come back in that order. So when it comes back in that order, you find that here again it will alter. This will become a north pole, this becomes a south pole. Now remember, that's the same thing happening this side. Like at the first time you had the south pole here and the north pole. In the second time when the current is going back, we shall have the north pole there and the south pole. Now that change in the magnetic flux in this side also induces another current in these coils on in the secondary coil. And the current induced in the coil once it is moving, now from Faraday's law, for any current moving which is changing to and fro, because even here the current will be doing the same. As the north to south, current will be becoming like that. That is current. South to north, current will be going up. Since current here is also changing, then there will be an induced EMF, electromotive force, which is measured in voltage. So that induced EMF here is the one which is supplied to the load, or which is supplied to the houses. And then, okay, it will be a bit safer because one is a step down transformer. Now, one would ask now, how does it bring it to be small? You find that this is the EMF, and this d theta here, d phi is our magnetic flux. Now, what you should know, the magnetic flux depends on the number of turns. If the number of turns is big, then even the magnetic flux will be very many. Say for example, like say here, here we have very many coils, so this one's here, maybe I'll erase off this. Okay, let's say for example, let's try counting the number of coils here. Maybe I have 1, 2, 3, 4, 5. Okay, maybe I'll count with this 6. So this side they have 6. Then I have how many? They are actually 4. Now what you should know is that since you realize that what happens is that the number of coils matters the amount of magnetic flux delivered, and from the Faraday's law, which says that E is equal to negative d phi over dt. Now for us we shall look at these two. Reading here. For us we shall look at these two. We shall look at this one and this. But where you seeing this, just put the letter n. So it means that the EMF is the equal proportional to the number of what turns, meaning that when the number of turns are very many, even the EMF will be very big. Now look here, since the number of turns were very many, there was some big EMF generated, which made the software to be, the soft iron core to be magnetized. Now to be magnetized, and the changing magnetic flux, what I was meaning that here I had south, north, then this time around again north, south. I explained that that kind of change in the magnetic flux induces an EMF in here. But since the number of turns are very small, the amount of EMF generated will be very also small, and which you are having the Vs, and then to be supplied to the load. And that explains why if you have here 13 kilovolts, this time around this side you can receive a 240 volts in simple terms. I hope that really makes some sense. Let's now go to part C. That's why here they're saying that when an alternating voltage moves through the primary coil, it induces a varying current which flows through the coil. Explain that. Next. Okay. Next, the saying the changing current induces a changing magnetic flux in the primary coil. Yes, the changing magnetic flux. Changing magnetic flux, I mean north, south, south, north, like that. The changing magnetic flux links up in the secondary coil. I explained that with less turns, which induces a lower voltage in the secondary coil. Okay, I hope that explanation really makes it a bit better. All right, good. Now we are now going to part B. Let's go and see what they want in part B. Okay, part B, the saying, I'll erase of this. Okay. Part B, the saying. Sorry. Okay, so part B, the saying. Explain to the landlord the cause of the low current in the house. Explain to the landlord the cause of the low current in the house. Now, what you must know, please, is here the cause of low current. Now look at this. Because now here in the house they connected using 10 ohm resistor and a 12 ohm resistor. And remember the house is oval. Now what you must know is, I'll use this, allow me use this area here. So the connection of the resistors matters a lot. Let's look at if resistors are connected in series. That's the first case. Then also when resistors are connected in what? In parallel. You want to see. So if resistors are connected in parallel, it will be in this format. Okay, get it here. Like that. The resistors are connected in parallel. Let's look at this. Okay, good. So the question was, explain to the landlord the cause of the low current in the houses. So they are receiving low current, and you all ever seen that. You realize that, especially, okay, and sometimes you find that okay, you may receive a low current in the house and realize that even if you try to turn on, even if you try to turn on the TV, it may not necessarily work. Even the phones can't charge. Now, I want to see what will bring this problem, please. Now, I want to look at the connections bring that, either the series arrangement or parallel arrangement. Let's look at the series arrangement. For example, I'll pick another color here. In the series arrangement, I'll pick another color here, please. Now, I'll put here my 10, then I'll put here my 12. Now, let's get the effective. Remember here, the PDV is 240 what? Volts. So you find that, how shall we get the effective resistance? Effective resistance, say R, will be equal to the sum of the two resistances, which will be a 10 plus 12. Okay, red ink is better here. Okay, we have 10 plus 12, where therefore effective resistance R will be equal to 22, okay, ohms, like that. But we know that from V is equal to IR, then we need to get the current. Why is the current very small, by the way? We want to judge and see which one is better. Is it series arrangement or parallel arrangement? We want to see by calculation. So I is equal to V over R in simple terms. So our current will be equal to, the V is 240 divided by the total PD, the effective resistance, which is 22. What will be our current produced here in parallel connection? So realize that our current will produced here will be 10. Okay, when you use the calculator, 10 point, actually allow me just call it 10.9. Those are amperes. That has been about the series arrangement. Let's see in parallel. Now in parallel, effective resistance R is got from, now we have that method whereby up you can get a product, then down you get a sum. So 10 times 12 plus, then over 10 plus 12. There is that method also when you have two resistors especially. Now please, one may ask, here we are still using the 10 ohm resistor and the 12 ohm resistor in both houses. Parallel arrangement, series arrangement. We want to see the amount of current produced in both. So our resistance here, effective resistance here will be, let's see. So our effective resistance here will be 5.45 ohms. Allow me use that. Now still from this formula of I is equal to V over R. Remember, we are connecting the same house which is receiving a 240 volts. Okay, so now from I is equal to a V over R, what are we going to have? Please, I'm getting it here that the other side you just go direct. To be 240 divided by a 5, okay, 0.45, a 5.45. And when you use your calculator, what do you get? Let's see here. When you use a calculator, what are you going to have in the long run? In the long run, you shall have 44.4 amperes. Now let's compare the two and we see which one is better. Let's compare and see which one is better of the two. This one here is series arrangement, gave us 10 ohms. Okay, parallel arrangement gave us 44. Now it means that whenever connecting a house, it is good to connect resistors in parallel than in series. Reason, the parallel arrangement gives us a bigger current, and that would be a very good reasoning as far as, okay, the explanation for the cause of the low current in the house. They would have used a parallel arrangement compared to a series arrangement. Let's go there and see the reasoning. Okay, so let's see that. Now shall we use calculations to get this done? So shall I say, shall we use the calculations to get this done? So shall I say, the houses were connected in series, which increased the resistance, leading to low current in the houses. Yeah, you all know that. Once you connect in series, increases, and once the increase in the resistance decreases the current. So like that, let's do that by calculation. So we have the resistors arranged in a parallel. We are getting them there. Okay, having the first resistor as 10 ohm. Okay, having the first resistor having, okay, that's our current passing through. Now the first resistor has 10 ohm, the second resistor has 12 ohms, but effective resistance will be equal to R for in series R1 plus R2. Then we shall get there. I'll explain this. Our effective resistance will be 22 ohms. The next from V is equal to IR, we shall have it as our V is 240 equals to I times 22, which is the effective resistance. Then when you divide both sides by 22, you find that your current I will be equal to 10.9091 amperes. That's the first version I've explained. Okay, next let's see. We are now saying that if they had been connected in parallel, let's see also, we repeat the process after connecting in parallel. We get the effective resistance in parallel will be 1 over R1 plus 1 over R2, or the product formula can work. Then we shall get our 1 over R is equal to that after substituting. Then our R finally, when we try to simplify, we get 5.4546 ohms. Okay, but remember our voltage is as usual 240 volts. Then from V is equal to IR, we shall substitute. V is 240 and our I times 5.4546 is our rate. Here, yeah, this is that, our R is there, please. Okay, now let's see how you get that. dividing both sides by 5.45. All right, this will get us there. Let's see. Our current I will be equal to 44 amperes in simple terms. Then you have to conclude and say, that's it. The houses therefore should be connected in parallel to ensure they receive more current. Okay, the same current, and a fault in one would not affect the other. By the ones you connect in parallel, a fault in one cannot affect the other. All right, I think that really makes some sense. Still again, let's. All right. Okay, and now this one has helped us answer part C. This has helped us answer part C because in our part B, okay, in our part B, remember now, okay, in our part B, they were asking whether what was the cause of the low current. The cause of the low current was they connected them in series. Then part C was asking for this. Okay, part C was asking, show with evidence. I want us to go through this. Show with evidence the modifications that could be made to ensure more current flows in the house. Now this is what I've explained here and here about the parallel and series arrangement. Those are the modifications. The modification should be, they should change from series arrangement to parallel arrangement. That is our part C we had just right here. The modification should be that the houses therefore should be connected in parallel to ensure they receive more current, but the same current, now here it means that if you have 4 rooms, all rooms will be receiving 44 amperes, and a fault in one of the rooms cannot affect the other, so it is a safer way, and it successfully answers our party. All right, it answers our part C, which said that show with evidence the modifications that could be made to ensure more current flows in the houses. The modification should be by connecting in parallel arrangement. Okay, please, at the end of this video, please, there will be another video which will pop up. Make sure you look at it. Okay, I wish you well. Have a nice time. Don't forget to subscribe, share to whoever finds this important. Okay, and also leave a comment. Please, I've said after this video there will be a video which will pop up there. You also click in it and watch it. You never need to be of importance. Our dream is to, by the way, our dream, we are not money minded, no, and that's why we provide this free service, such that someday we benefit. Actually, we benefit from each other, because I know there's some people who are there and they hardly receive some of this information here, but once we put it forward in the platform here like this, we all share knowledge. Feel free to inbox. We have my WhatsApp number there on the screen, or for any business in one way or the other. Thank you.